बता दे पूरा आ रहा है बिफोर माइनर पूरा आ रहा है आते भाई 9 चैप्टर हो गए बुक्स है ये 9th चैप्टर खत्म हो रहा है मतलब 3rd नहीं और 6th आई एम नॉट श्योर 6th का थोड़ा बहुत हुआ है बाकी 9th चैप्टर 170 पेजेस ये कोर्स में विड्रॉ होता है दिख रहा है
In the last class, we started looking at qualitative response of the system. We said the transfer function G of S. Transfer function is nothing but the equation which relates your output to the input. The definition of the transfer function is Laplace transform of output in a deviation form divided by Laplace transform of input in a deviation form. That is given as a transfer function, isn't it? So the transfer function can be represented as y dash s by f dash s, where y dash s is nothing but the output in a deviation form and f dash s is nothing but the input in a deviation form. I can rearrange this equation and I can find out what is y dash s. So y dash s comes out to be g of s into f of f dash s, isn't it? Correct. And we can invert back this equation in a time domain and we can find out how y is varying with respect to time. Isn't it? That is what we have seen in the last class. We said in this particular equation, G of S is actually coming from the equations. Isn't it? G of S is actually coming from the model equation. Whereas F dash S is the input. So it is coming from the external environment. Isn't it? I have no control on the external environment. What input is coming in, I don't know. But process I can figure out. I can look at G of S a little bit more closely and I can conclude whether the given system is stable, unstable, or whether the given system is going to give you oscillatory behavior or exponential behavior. This type of qualitative information of the process you can find out. Of course, the actual output also depends on f dash t, isn't it? Actual output depends on f dash s, isn't it? But I am saying that f dash s is coming from the external environment. I don't know what type of input it will have, whether it is sinusoidal input, step input, impulse input, or any other input, isn't it? I don't know. But this G of s I know. G of s I know because this is coming from the equation. So G of s is actually coming from the physics of the system. So I can look at the G of s little bit in more detail and I can find out what type of qualitative response I can get from G of s, isn't it? So that is what we have discussed in the last class. Then we said we will look at the G of s term little bit in more detail. So what we said is, remember the G of s is also going to be a ratio of two polynomials, Z of s divided by P of s. Z of s is nothing but the polynomial which is there in the numerator, isn't it? And if I find out the roots of this polynomial, then these roots are referred as zeros, and that is the reason why we have denoted the numerator by z. Okay. Similarly, the denominator P of s, if I put P of s equals to 0 and find out the roots, these are the roots actually called as poles of the transfer function. These are called as poles of the transfer function, and that is why the denominator is represented by P of S. Okay. Now in this case, the P of S is having these 5 roots, isn't it? So we are having 2 distinct and real roots. So P1 and P2 are the distinct and real roots. Then we are having P3 and P3 dash. These are complex conjugate roots. That's why these are occurring in pairs. Then we are having P4. P4 is a multiple root. So there are multiple roots occurring exactly at P4. There are, in this case, we have taken M roots occurring. And the last root, which is P5, this P5 is located exactly at the origin. So if I go back and see where these roots are, so you can see that P1 is here on the left hand side of the imaginary axis. So P1 is having the negative real part. You can see this P1, this is an imaginary plane, isn't it? This is a complex plane. So here you can see that P1 is on the left hand side of the imaginary axis. So that means it will have a negative real part. P2 is located on the right hand side. So P2 is having a positive real part. Then look at P3. P3 are the complex conjugate roots. So that is why they are occurring exactly as a mirror image of each other, isn't it? Then P4 is a multiple root. So there are multiple roots occurring here, isn't it? And P5 we have taken exactly at the origin. So these are the location of all the roots. Now let's look at each of these roots little bit in more detail. We started with this P1 and P2. We said P1 is having a negative real part, P2 is having a positive real part. So if I represent this particular equation in terms of partial fraction, I will have C1 divided by S minus P1, C2 divided by S minus P2, plus C3 divided by S minus P3, plus C3 star divided by S minus P3 star, and these are the multiple roots represented here. Okay, and the last term is C5 divided by S minus C5. And I can invert all these terms back into time domain and see what type of response in a time domain I am going to get if t tends to infinity. This is what I am trying to understand. Okay. So let's look at this first root P1 and P2. So we said that P1 is having a negative real part. So if I invert this first term into a time domain, what I am going to get? I am going to get C1 e raised to the power P1t. That is what the inverse Laplace transform of this first term I am going to have. Isn't it? So clearly, this is the term I am going to get, and now in this particular term you can see that P1 is less than 0, because P1 we are assuming that it is located on the left hand side of the imaginary axis. So what will happen to this entire term when t tends to infinity? When t tends to infinity, this term is going to become 0. So what it means is, if there is a disturbance in the system, the effect of the disturbance will die out as t tends to infinity. Isn't it? What it means is, when t tends to infinity, whatever the impact this disturbance is having on the system, that impact is going to die out. Isn't it? That is why my output is going to become 0. Remember, all the variables we are taking it in a deviation form. So if my output is coming out to be 0, what it means is, I have came back to the steady state value. That is what it means. Isn't it? Now let's look at the second term. P2 is greater than 0. That means this second root is located on the right hand side of the imaginary axis. It is having a positive real part. If I invert this particular term into a time domain, what I am going to get? I am going to get C2 e raised to the power P2t. Now again in this particular equation, if I put t tends to infinity, what is going to happen? This e raised to the power P2t is going to become infinite. It is going to become infinite. So that means your output is going to become infinite. So whenever there is a change in the disturbance, and if your output is becoming infinite when t tends to infinity, what it means? Unstable. It means your system is unstable. Isn't it? So with this root I am going to get an unstable system. Now let's look at P3 and P3 star. P3 and P3 star, these are the complex conjugate roots. Whenever we have a complex conjugate root, we get the response which is periodic in nature, isn't it? So with respect to both these roots, the response we are expected to get is this, e raised to the power alpha t sine beta t plus phi. Okay, so these are the periodic terms. You are going to get a sine wave. Now this sine wave, whether this sine wave is increasing or decreasing, it depends on what is the value of this alpha. If this alpha value is negative, in that case what will happen? You will have a sine wave initially, but this sine wave is going to die out with time. So that means your system response is going to become stable when this alpha is less than 0. So what it means? It means that if your complex conjugate roots are located on the left hand side of the imaginary axis, in that case my system response is stable. You can see these are the P3 and P3 star. You can see these are located on the left hand side of the imaginary axis. That means their real values are negative. So you can see that this response is dying out with time. The response is dying out with time. Okay. But let's say these P3 and P3 star are located on the right hand side of the imaginary axis, somewhere here, let's say, with a positive real part. With a positive real part. What is going to happen? With t tends to infinity, your sine wave is going to increase. The amplitude of the sine wave is going to increase. And whenever that happens, what it means? My system response is becoming unbounded. And when the system response is becoming unbounded, what it means? It means that the system is unstable. Isn't it? So that is what is happening. You can see the system response is becoming unbounded here. And your response is unstable. Okay. Third case is when these two complex conjugate roots are located exactly on the imaginary axis. When these are located exactly at the imaginary axis, what it means is their real value, their real part is 0. Only the imaginary part is there. Isn't it? In that case, I am going to get a sustained sine wave. I am going to get a sustained sine wave like this. So whatever the amplitude I am having, the same amplitude will continue. It will not die out. It will not increase. But that's okay. Isn't it? It's not becoming unbounded. So what we call such systems as critically stable or marginally stable. Okay. So that gives a very interesting conclusion here. The interesting conclusion here is if we are obtaining the roots of the polynomial P, and if these roots are located on the left hand side of the imaginary axis, if all roots are located on the left hand side of the imaginary axis, then my system response is stable. But if any of the root of P of S are located on the right hand side here somewhere, then my system response is unstable. And whenever the roots are located on the imaginary axis, then the system is marginally stable or critically stable. Is it clear to everyone?
Yes.
So this is what the conclusion we are going to come back again and again. So whenever we will have a transfer function, we will find out the roots of the denominator, and if these roots are located on the left hand side of the imaginary axis, we will conclude that the system response is stable. If it is located on the right hand side, system response is unstable. And if these are located on the imaginary axis, they are critically or marginally stable. Okay. Is it clear to everyone? Yes, no?
Yes.
Okay. Now let's look at the this multiple pole case. So there, remember we have one more root which is a multiple root. So P4 is a multiple root. There are m roots are occurring at P4. Isn't it? So whenever I have a multiple root, the partial fraction is represented like this, and if I invert back this into a time domain, what I am going to get? I am going to get e raised to the power P4t into, there will be one more additional term in terms of time, isn't it? There will be one more additional term in terms of a time like this C41 plus C42 divided by 1 factorial, and how many terms are there, how many multiple roots are there depending on the number of p terms you will be having here. Okay. Now if you look at this particular equation, if this P4 is negative, if this P4 is located on the left hand side of the imaginary axis, what will happen when t tends to infinity? This entire term is going to become 0. Isn't it? So whenever P4 is located on the left hand side of imaginary axis, this term is going to die out. That means system response is stable. Another case is, let's say this P4 is located on the right hand side of the imaginary axis, that means P4 is positive, then my system response is unstable because this term is going to become infinite when t tends to infinity. The interesting case here is when this P4 becomes 0. And this is what very often asked question in the gate examination or in interview. So remember what we have concluded just a while ago. We have concluded that whenever the roots are located on the imaginary axis, my system response is critically or marginally stable. But that is not true for this case. It is not true for this case. When this P4 becomes 0, that means the multiple root is located on the imaginary axis. In that case, when t tends to infinity, this particular term is going to become infinite. That means if the multiple root is located on the imaginary axis, multiple root is located at the origin, in this case, more precisely, then my system response is unstable. It is not marginally stable, it is unstable. Okay. So the conclusion which we have drawn is what? When the roots are located on the left hand side, system is stable. When located on the right hand side, system is unstable. When the roots are located on the imaginary axis, these are marginally stable only and only if there is no multiple root. If the multiple root is there, in that case system response is unstable. Okay, this is a small caveat here which you have to remember. Is it clear to everyone? Okay, now let's look at the last case. This is the last case. Now, the last case is when the root is located exactly at the imaginary axis, at the origin. In that case, this P4 is 0. So what we are going to get? C5 by S. If I invert C5 by S, what I am going to get? Just C5. Isn't it? That means my output will be constant, and that will be exactly equal to C5. It is not going to increase, it is not going to decrease. So what it means? Stable. Is it clear to everyone? Okay. So this is what qualitatively plotted. This particular plot is really interesting. If you remember this, then you understand the stability. There will not be any confusion in the stability. Okay. All right. Is it clear to everyone? So this is all about the basics which we wanted to cover in this course. Now we are going to start the process control. So whatever we have covered so far, was kind of in a way these are the bits and parts which we wanted to understand before we can go to control. So we are starting with the control from this class onward. This is the formal control. So we will be starting from first order process. Okay. So first order process, the question here is what a first order system is and what physical phenomena give rise to first order system, what its characteristic parameters are, and how it responds to various changes in the input variable. So these are the three questions we wanted to answer. First question is what is first order process? So first order process is a process which is governed by a first order differential equation. So if you are writing a model equation of a system and the model equation of a system is a first order differential equation, then the system we are calling it as a first order. Okay. So this, let's say, typical differential equation, first order differential equation is given here. A1 dyt by dt, a0 yt equals to b f of t. Here yt is the output and f of t is the input. Again, let's assume that is a0 is not 0. A0 is non-zero. Okay. In that case, I can divide this entire equation by a naught. You will get a1 by a naught. dyt by dt plus yt equals to b by a naught f of t. And this a1 by a naught, we are defining this as a time constant of the process. Time constant of the process, which is denoted by tau p. Remember last time when we have seen this certain heater system, there also we have defined tau p, kp, kd, and I said we will come back again and we will look at more details on what tau p is, what kp is, and what kd is. So here tau p is a time constant of the process. Again we will come back to the physical significance of tau p, kp, and kd. Okay, so tau p, as name suggests, it gives the speed of response. We will prove that. Why I am saying it gives a speed of response. We will prove that. Okay. So in this case, a1 by a naught is defined as time constant, whereas b by a naught is defined as kp. Kp is nothing but steady state gain, static gain, or simply we call it as a gain of the process. Okay. So these are the parameters of the first order process. So first order process has two parameters. One is tau p, which is nothing but the time constant of the process, and kp is a gain of the process. Okay. Is it clear? So kp is defined as change in the output at steady state divided by change in the input at steady state. We will come back to this definition again. Okay. So in this particular system, if I apply the Laplace transform, I will get tau p ys into s minus y0, but we are assuming that this differential equation is in a deviation form, so y0 is 0, isn't it? So tau p ys into s plus ys equals to kp f of s. I can take ys common. I will get on the left hand side tau p s plus 1. So ys will be given by kp divided by tau p s plus 1 into f of s. So that is what is written. Ys by f of s is given as kp divided by tau p s plus 1. So you can see that the first order process is characterized by this equation, which is nothing but the transfer function of the process. Transfer function of the first order process is directly written as kp divided by tau p s plus 1. We will not derive this now onward. Whenever we will say first order process, we will write directly the Laplace transform of first order process is kp divided by tau p s plus 1. That's it. Okay. So this is the transfer function of the first order process, which is given as ys divided by f of s. Ys is the output in the deviation form divided by f of s, which is nothing but the input in a deviation form. That is the standard definition of transfer function, which is given as kp divided by tau p s plus 1. I can get this equation directly by taking the Laplace transform of this equation too. Is it clear to everyone? Yes, no? How many of you are not able to understand what we are doing? Please raise your hand. Acha, I rephrase the question. How many of you know what we are doing? So rest, I can assume that they are not knowing, isn't it? Is that correct? So please go through the material. If you are not able to understand this course, take my word, you will not be able to get anything, isn't it? So please go through the material. Everything is there in the book. I have given you the PPT also, isn't it? There are 300 slides we have to cover. Correct? So please go through the material. And don't be in the wrong illusion that you will be able to solve the question paper just because the examination is open book. I am telling you that that is not going to happen. I have seen that very often the solution is there in the book, but you will not be able to find out because that's a big book. Where you will search? Backside in the index you will not get. Okay. So please go through the material. My sincere request to all of you is please go through the material. And if you are not able to understand anything, please feel free to ask me. Please ask me in the tutorial class, in the regular class, you ask me, and I am assuring you that if you ask me 100 times, I will not hesitate to explain 101 times. Okay, so please ask. If something is not clear, please ask. Okay, so we are we have obtained this first order transfer function, which is given as Kp divided by tau ps plus 1. Okay. Now let's look at slightly modified case. Slightly modified case is, this is the equation we have. We have started with a naught is not equal to 0. Let's say this a naught is equal to 0. This a naught is equal to 0. In that case, my equation will be dy by dt is given as b by a1 f of t directly, isn't it? And that can be represented as this b by a1 is represented as kp dash. I can take the Laplace transform of both the sides, and if I rearrange, my transfer function comes out to be ys divided by f of s, which is nothing but kp dash by s. Okay. And this particular process is referred as pure capacitive process. This is referred as pure capacitive process. Why this word pure capacitive is? We will again come back. Don't worry. Okay. So it is referred as pure capacitive process. Now, both these transfer functions we are going to look at it in more detail. See, this is the transfer function which is obtained when I am having a regular first order function. This particular transfer function we have obtained when I am having a pure capacitive process. Okay, pure capacitive process in the sense that there is no denominator, is not tau ps plus 1, it is just s. Okay. Another interesting thing to note down here, when we get s in the denominator, anyone? When we get s in the denominator? Just 1 by s term, when we get 1 by s?
Constant.
Function is constant. So kp by s, isn't it? So that means in this case, this kp dash is there, and if you multiply this f of s, let's say this f of s is again a constant term. So I will have 1 by s term. I will get 1 by s square term in the denominator. And if I invert back, what will happen? I will get t term, isn't it? So that means as the t increases, this output will continuously increase. This output will continuously increase, isn't it? Correct? So you can figure out that how your output is going to, what will be the qualitative nature of your output directly by looking at the transfer. How about this? How about this? I will have 1 by s term here because of this f of s. If I invert back, this particular term will lead to exponential term, isn't it? So in this case, my output will be exponential output and it will settle down to some value, isn't it? Correct? So you can see that you can qualitatively figure out how your output is going to be just by looking at the transfer. Is it clear to everyone? Another thing to note down here is, typically 1 by s term we get when we are looking at the Laplace transform of integral. Laplace transform of integral is 1 by s term comes out. And when we take the Laplace transform of derivative, we get s term in the numerator, isn't it? So what it means? It means that whenever, so see, when you look at the derivative has a predictive quality, anticipatory qualities derivative has. So whenever you have s in the numerator, it actually anticipates your future, and whenever you have s in the denominator, it is actually integrating. Okay, this is how qualitatively you have to understand the equations here. Alright? Okay, let's look at these two equations a little bit in more detail. Now, remember in this case, if you look at the first order system, first order systems are characterized by two things. First order system you get whenever you have a capacity to store mass, energy, momentum, etc. And if you are having a resistance to throw up this quantity, then you get the first order. Okay, please hear me out of this. So first order process, when you get the first order differential equation, actually you get the first order differential equation if your system is having a capacity to store mass, energy and momentum. resistance to flow of these quantities. In that case, you get the first order. Okay. So you can see that the system is acting a buffer between inflow and output, and in between there is a capacity to store and resistance. Alright. Typically, if you look at the systems like tank, so tank is having a capacity to store the mass, and how much is going out from your tank depends on how much is the hydrostatic head present in the tank. Remember, if you are having a tank and if you let's say have a hole in the bottom, your flow rate coming out from your tank depends on how much hydrostatic head you are having. Isn't it? Correct? More accurately, it depends on under root of H, if I recall the fluid mechanics. Isn't it? Correct. So in this case, you can see that the entire volume and the area that has a capacity to store the mass. But this hole which you have made in the bottom, it has a resistance. It's not all the material is coming out at a time. It is actually providing some resistance to the flow. Isn't it? So you will see that all the first order processes, they have capacity to store the mass and they have the resistance to the flow of mass, energy and momentum. In that case only you get the first order. Now let's come back to this system. This system has only the capacity to store. They do not have a resistance. That's why this particular process is called as pure capacitive process. Now are you able to get why this word pure capacity is used? Because there is no resistance in it. That resistance is actually coming from which star? That resistance is actually coming from this star. Okay. And we will come back to this particular point why I am saying this particular term is coming from the resistance. We will come back when we will look at the same tank system again. Okay. The last point is first order system are most common in chemical engineering, CSTR, Clipchamp, all these are first order. So, okay, when you have written the balance equations, you have written the balance equations in terms of what? Mass balance, energy balance, and momentum balance, and component balance. So only these three things are going to give you a differential equation. Second order and, okay, I'll come back. Second order we have not much time. When we can get a second order term you get, second order system you get whenever there is inertia. So whenever you have an inertia, okay, inertia means what? Rate of change of. So velocity is change of distance by time, isn't it? Correct. And velocity is momentum is mass into change in velocity by time, isn't it? Correct. So you can see that in this case you are bound to get a second order difference. So you can get a second order process whenever there is a inertia associated with it. Not another. Okay. Again, whatever you said. So typically you get a first order process. But let's say there are two first order processes in series. Then two differential equations are coupled. So if you look at them, they are actually second order differential. So in that case you can get a second order. And we will come back to this particular discussion again when we will look at a second order system. So there are three types of second order processes we can get. Multiple first order processes in series. Then the system which is having the inertia term, all such systems give inherently second order system. And there is a third case which is a first order system associated with a controller that can give you a second order. So we will again come back to this discussion later. Okay, is it clear? Okay. Now let's look at this tank system again. So in this particular case, there is a Fi coming in, which is the inlet flow rate to the tank, isn't it? Outlet is F0, isn't it? The height of the liquid present in the tank is H, and the resistance to flow of this material from this tank is denoted by R. Okay. Now in this case, if you look at the model equation which we are expected to get in this case is A dx by dt is given as Fi minus F naught. Fi minus F naught. This particular model equation we have derived earlier, isn't it? In this case, this Fi which is coming as an input here, so we will keep this Fi as it is. How about F naught? The outlet flow rate. Outlet flow rate here actually depends on how much is the hydrostatic head present in the tank, isn't it? Actually, it is proportional to under root of H. But just for a simplicity, just for a simple analysis, let us assume that it is only proportional to H. Just to understand. Actually, if you look at it, if you derive based on the fluid mechanics, it is proportional to under root H, not H. Okay. So let's say if we are assuming that this flow rate is proportional to H, that proportionality constant. In that case, you can see that this F naught is given as H by R. So 1 by R is the proportionality. That is the resistance. We are representing that resistance. That's why we have taken this as denominator. Okay. Is it clear to everyone? So you can see that this outlet flow rate, I can write down this as H by R. Correct? So this is H by R. Now, if I rearrange this term, if I multiply this entire equation by R, what I am going to get AR dS by dt, and this H which is actually coming from resistance to flow, isn't it? That is actually coming on the left hand side. So you can see this H added H is actually leading to the resistance here. Isn't it? So remember, in the pure capacity process, this term is not there. There is only a capacity to store the mass. In this case, not only the capacity to store the mass is there, but also there is a resistance to the flow. Clear? Now, in this particular equation, AR dS by dt plus H equals to RFI, I can again come back to the same definitions which we have used earlier. So, AR I can represent as time constant tau p. AR is represented as time constant tau p. So this equation becomes tau p dH by dt plus H is given as, and this right hand side R I can represent as Kp. So that becomes Kp into Fi dash. Correct? And if I take a Laplace transform of this entire term, then I can get G of S, which is nothing but the output in deviation form divided by input in a deviation form. So that comes out to be Kp divided by tau ps plus 1. So this is the standard transfer function we expected to get in the first order process. Isn't it? Remember, I said the first order process is characterized by this equation. Whenever I have a first order process, I will directly write down the equation which is nothing but Kp divided by tau ps plus 1. Now in this case, what is tau p? What is tau p? Tau p here is A into R, isn't it? Where A is nothing but what? The area of the cross section. More is the area, more amount of material you can store. So A is nothing but what? Capacitance to store the mass. Here A is nothing but capacitance to store the mass. And what is R? R is the resistance to flow of the mass. So time constant is nothing but what? Time constant is nothing but multiplication of capacitance into resistance. Capacitance into resistance is nothing but the time constant. Okay. Correct? And when we look at the pure capacitive process, in a pure capacitive process, we only have capacitance, we do not have a resistance at all. Okay? Is it clear to everyone? Clear, yes or no?
Yes.
That under root of H you are saying, na? That we will come back. I am taking this particular case simply because if I take the under root of H, then it becomes a non-linear. So I wanted to avoid the non-linear equation in the starting. We will use under root H later because the correct equation here is under root H. If you follow the fluid mechanics correctly, you will get your outlet flow rate which is proportional to under root H, not H. But just for a simplicity, we are taking it is proportional to H so that we can understand the concept. Later on, we will have under root H. Okay, and we will linearize it. So that we will do it as we go ahead. But I don't want it to add the complexities in the starting itself. Let's start with a very simple thing. Slowly we will move to the more complex cases. Okay, is it clear to everyone? Yes, no? Okay. एक ही आदमी को समझ में आ रहा है क्या? बाकी लोग को क्या है? Is it clear to everyone? Yes, no? Backside all are sleeping. अरे भैया अभी तो सुन लो, कान में लगा कि क्या सुन रहे हो आप? कोई स्पेशल रिक्वेस्ट हो तो बताओ, डायरेक्टर कोई लेटर लिखेंगे कि आपके लिए कुछ एकदम बढ़िया यहाँ रिक्लाइनर बेड वगैरह लाया जाए, यू कैन एंजॉय हियर, ऐसा कुछ है कि कोई एक आदमी रखे कि डायरेक्टर को ये रिक्वेस्ट करे कि आपके लिए एक मतलब एक एम्प्लॉय हायर करे जो आपके लिए क्लास में बैठेगा, हवा वगैरह करेगा, ऐसा कुछ है? ऐसा नहीं है तो ध्यान दो इधर, अगर ऐसा नहीं है तो ठीक है। बेटे आप भी अब तक सोए ही हो, नींद से कब जाओगे? और कौन कितने लोग सो रहे हैं? कब जागोगे नींद से? इतना जोर से चिल्ला चिल्ला के मैं बोल रहा हूं फिर भी नींद आ रही है, सरप्राइजिंग। Here we are. So time constant is given by resistance to flow and capacitance, isn't it? Capacitance multiplied by resistance will be the time constant. Remember I said time constant gives you the speed of response. We have not gone there. We will go there. Very soon. Okay. Now let's look at the pure capacity process. Remember I said in a pure capacity process there is no resistance. There is no resistance. So now this is the same system. The only difference here is the outlet. Outlet is coming from the pump. So outlet is not dependent on the hydrostatic head. It is coming out from the pump. Irrespective of how much the hydrostatic head is there, the pump is going to give you output more or less fixed. Not going to change. Not going to change. Correct? So there is no resistance here. There is no resistance to flow. Because this output is directly coming from the pump. If I write down the balance equation in this case, what I am going to get? A ds by dt is given as Fi minus F0, isn't it? And ds by dt, if I rearrange Fi minus F0 by A, isn't it? In the steady state, this will be given as Fis minus F0 by A. I can subtract this equation from this, I will get the equation in a deviation form. That is, ds dash by dt is given as Fi dash by A. Unlike the previous case, in the previous case when we find out the equation in a deviation form, you can see we get this h dash term here. Why we are not getting that type of term here? Because this F0, what will be the steady state value of F0? F0, I am saying. What will be the steady state value of F0? F0 is the output and it is coming from the pump. So whether there is a disturbance, no disturbance, that F0 will remain F0. It's not going to change. Isn't it? It's a steady state value itself. So if I subtract this particular term here, this F0 will get cancelled out. Remember, when I have written this equation in a steady state, I have written this particular term as Fis, but I have not written this as F0s. It is F0 only. There is a small difference, and these small differences, small changes, you are most likely to miss. Okay, that I know from the experience that you are likely to miss this term. So this F0 remains F0. If you subtract, this F0 will get cancelled with this F0. You will have this Fi minus Fis divided by A, and that becomes Fi dash by A. So you can see here you are getting Fi dash by A. So there is no resistance now. If you apply the Laplace transform here, what you get? Kp dash by S directly. Kp dash by S. You are not getting tau ps plus 1 in the denominator. So this is a pure capacity process. If you revert back for a step input, let's say this FIS is a step input. So FIT is a step input, that means what? FIS will be 1 by S. If I multiply this FIS with this equation, that becomes Kp divided by S square. Kp dash divided by S square, isn't it? And if I invert that into a time domain, S dash C is given as Kp dash C. So you can see that in this case, as there is a disturbance, as there is a small disturbance in Fi, in that case the height of the tag will continuously increase. Okay, is it clear? But unlike this, if you look at a first order process, unlike this, if you look at this particular process, if there is a step input in FIS, we will have 1 by S term here. And if you invert that into a time domain, what you are expected to get? You are expected to get Kp 1 minus e raised to the power minus c by tau t. That is what you are expected to get. Isn't it? So what it means? It means that your response will be exponential and it will become constant. It will not continuously increase. Okay. That is the difference. Is it clear to everyone? We stop here and we will again continue from this point. Okay? And please go through the material. I am again and again requesting and change your sleeping habit. Please sleep in 9 o'clock in the night and come with a fresh mind in the class. Okay?
ट्यूटोरियल 2 बजे है। ट्यूटोरियल आज है 2 बजे।
दोनों बैच के साथ ट्यूटोरियल है। दोनों बैच के साथ
1 and 4
नया तू हंसा देता है क्लास में,
ऐसे बात कर रहा है,
कुछ भी करता रहता है।
You know what you see?